Welcome to our guide on wastewater treatment. Today, we will explore the critical process of transforming wastewater into an environmentally safe effluent. Wastewater treatment is vital for protecting our water resources from pollution, ensuring public health, and maintaining ecological balance. My colleague Julia and I will dive into the two key stages of wastewater treatment, the primary separation process, and the secondary, conventional active sludge process, each playing a unique role in the purification of water. We will start with an overview of each stage, but our focus will be on the importance of the active sludge. In the primary stage, screening and pumping of the larger objects takes place. A metal grating captures large debris, followed by a moving screen filtering out smaller items. Thereafter, in the grit chamber, heavier particles like sand and gravel settle down. The primary settling tank, or clarifier, allows about half of the suspended organic solids to settle as sludge, which becomes the primary sludge. The sludge is the residue that accumulates in sewage treatment plants.
While primary treatment involves removing material through physical means, the secondary treatment process utilizes microorganisms to remove contaminants from the influent. This can be done through various methods: running influent through a trickling filter bed, an aeration tank, or sewage lagoon. Each of these methods involves creating carefully controlled environments where these microorganisms can grow. Aeration tanks are the most common secondary treatment method in the United States. This is also known as the activated sludge process. This method involves pumping influent into a tank containing a bacteria-rich slurry, which is known as the activated sludge. High-purity oxygen is then pumped through the mixture, promoting bacterial growth and the decomposition of organic material. This mixture is then pumped into a secondary settling tank where the sludge settles at the bottom and the water is siphoned from the top. The detention time in an aeration basin varies from 4 to 8 hours. This process must be meticulously monitored and controlled to maintain the proper ratio of substrate, organic load to microorganisms, food to microorganism ratio. The waste rate or wasting rate determines the FM ratio. The higher the wasting rate, the higher the FM ratio. Hence, lower F to M ratio means the microorganisms in the tank are starving, which results in more efficient wastewater treatment. Important parameters are as follows: organic loading rates, oxygen supply, and control and operation of the final settling tank. The microbial biomass produced in the aeration tank must settle properly from suspension so it can be either wasted or returned to the aeration tank. Moreover, good settling occurs when sludge microorganisms are in the endogenous phase, which occurs when carbon and energy sources are limited and the microbial specific growth rate is local. This explains why a lower FM ratio results in more efficient treatment. Additionally, poor settling may cause sudden changes in temperature and pH, absence of nutrients, and presence of toxic metals. Recycling the activated sludge biomass allows for larger quantities of microorganisms to oxidize organic matter quickly. As mentioned before, this activated sludge/slurry goes back and forth between the aeration tank and settling tank. The content of the aeration tank is known as the mixed liquor suspended solids, MLSS. The organics in the MLSS are called mixed liquor volatile suspended solids, MLVSS. The MLVSS is made up of non-microbial matter and dead and living microorganisms. To maintain this process, the food-to-organism calculation needs to be done, where Q is the flow rate of sewage, in million gallons per day. BOD5 is the 5-day biochemical oxygen demand, milligrams per liter. MLSS is the mixed liquor suspended solids, milligrams per liter, and V is the volume of aeration tank, in gallons. For the routine operation of the sludge settleability, the sludge-to-volume index is determined by multiplying the volume of the settled sludge after 30 minutes by 1,000, and thereafter dividing by the MLSS amount.
The activated sludge process can also be modified for nitrogen removal, to encourage nitrification followed by denitrification. By modifying the biochemical oxygen demand load, mixed liquor suspended solids, and retention time, a nitrifying population of microorganisms can be established. The growth rate of nitrifying bacteria must be higher than the growth rate of heterotrophs. Hence, nitrification is expected at a sludge age greater than 4 days, and denitrification must follow nitrification in order to remove nitrogen from the wastewater. There are two common processes used for nitrogen removal: single sludge and multi-sludge systems. The single sludge system involves a series of aerobic and anaerobic tanks in lieu of a single aeration tank. In a multi-sludge system, carbonaceous oxidation, nitrification, and denitrification are carried out in three separate systems. Added methanol or settled sewage serves as the source of carbon for denitrifiers. The activated sludge process also allows for the removal of phosphorus. The process follows aerobic and anaerobic processes known as EBPR, where microbes use the phosphorus in the aerobic phase and release it in the anaerobic phase. This release increases the energy in the system, to be used in the uptake of biochemical oxygen demand, BOD. Following secondary treatment, wastewater is disinfected. In this stage, the water is disinfected to remove any pathogens or disease-causing microorganisms. This is done mostly by chlorination and ultraviolet radiation. After this process, the disinfected water is now ready to be released into the open water and to the homes of people for use.
The active sludge collected from the primary and secondary stages as waste are placed into tanks known as digesters. These digesters are set to conditions optimal for microorganisms, low in oxygen and 98 degrees Fahrenheit. These digesters allow microorganisms to process the sludge, converting it into methane gas. The remaining solids are removed of all water and are used in agriculture as fertilizers.
Water treatment is important in maintaining the ecosystem and keeping our water clean. Microorganisms are extremely efficient at removing pathogens and other chemicals. This is why they are used as the main treatment component throughout the process, and the reason we never have to worry about what happens with our waste after it leaves our homes. I hope you guys learned something new today. Thank you for your time.
Thank you for your time. Bye.